Hello, my name is Marcus Beck. I am the senior scientist at the Tampa Bay Estuary Program, and this talk is about how we are developing indicator products around climate change using global data sets to hopefully inform regional decision making around these topics. So, if you're not familiar with Tampa Bay, it is generally considered a management success story due to the long-term recovery of water quality and seagrasses in the bay. And this success is largely the product of our management paradigm that seeks to control external nitrogen loads to reduce algal production in the water column to promote a light environment that will support seagrass growth. And if you look at the historical nitrogen loading in the bottom left in the 1970s compared to presently, you'll see that we've reduced external nitrogen loads by about 2/3. And this bar graph on the bottom right shows the long-term recovery of seagrasses as a result of these reductions in nitrogen loads. So that is the success story. However, you'll notice from our all-time high in 2016 for seagrass coverage, we've seen successive declines with each year of mapping for seagrass coverage. So this is a concern. Why have we lost these seagrasses despite the fact that nitrogen loads and water quality generally remains supportive for seagrass growth? So, of course, the question is, what has been the role of climate change? Recently, in the last couple of years, specifically, we've had very, very hot years, and there have been a lot of questions around how climate change has been influencing seagrass resources in Tampa Bay. On the bottom left, you'll see basically the long-term time series of air temperature at Tampa International Airport, kind of your typical story of temperature increase long-term. And that has obviously, like I said, led to some concerns about how that is influencing resources in the bay. As noted by interest in the media in the bottom right here, just showing an article of basically posing this question: how is climate change or hot water influencing seagrass recovery? Now, this is problematic, not just in and of itself, but how this interplays with management paradigms that we've been using for a long time. So basically, with any kind of climate stress, we know that water quality goals are less likely to be met. So this plot on the right kind of shows a hypothetical example of essentially with our conventional management paradigm, we know with some level of certainty if we have nitrogen loads below some level, we are having some fairly high probability of meeting some water quality goal, whether that's chlorophyll A concentrations or seagrass growth or whatever. But if you impose climate stress on this, our probability of meeting that water quality goal is going to be much less, just because that is an added stressor that is making our effectiveness of these conventional approaches much less. So that is a concern. We want to know how that's going to influence our existing management approaches and what we can do about it. Now, a little bit about Tampa Bay, the estuary program in particular, how we operate and what we do to make sure the bay is in a healthy and resilient state. We're kind of in the middle here. This is our structure of our management conference. Really, we're kind of just an unbiased broker of science to inform a scientifically sound and community-based management plan for the bay. So we have technical advisory committee that vets a lot of the science, community advisory committee that shares concerns with the public about how the bay is trending, and nitrogen management consortium that deals with basically controlling some of those external nitrogen loads. And information from these groups gets funneled up to our boards at the management level and policy level. Of course, we are working with a lot of people, and to support this work, we have a lot of different indicators that report on status and trends of different aspects of bay health. So this is just a snapshot of some of our existing indicators related to water quality, benthic health, fisheries health, seagrass, tidal creeks, habitats in the watershed, and bay sediments. Now you'll notice one thing that's missing from here is, of course, climate change. And so we want to fill that indicator gap. Before we can do anything about climate change, we've got to know what is happening in the bay itself. And so we have in one of our strategic planning documents for a comprehensive and conservation management plan, the CCMP, calls out this specific gap for the analysis and synthesis of long-term regional climate characteristics. So we want to know things like, is sea level rise changing? Is water temperature changing? How is rainfall changing? How is the number of extreme storm events changing? Are they increasing, decreasing, maintaining stability? This is information that we know is out there, but not synthesized in a readily accessible format. So we wanted to fill that gap. And our general approach of doing this followed these couple of these principles here to basically building a data pipeline to synthesize data sets into a distilled, easily communicable format. So we wanted to focus on indicators of climate change that were, of course, relevant to both people to inform the public, as well as descriptive of things that might affect the ecology of Tampa Bay. And this should have a broad spatial coverage related to both the watershed as well as Tampa Bay and the Gulf of Mexico itself. The data that we're using should be from publicly available sources, shouldn't be behind any kind of paywall because we want to be able to update it on a regular cycle. It should have a long-term record so we can compare current status relative to what it's been like in the past. It should be updated on a regular basis, should be authoritative, etc. Now, the methods we're using to distill this information, 100% using open source tools to do this in line with our open science approach that we adopt as a program. We're building routines in open source software that we've developed primarily using R. The idea being that essentially the synthesis process from data to information is going to be reproducible. Now, the visualizations that we're using to distill this information should really provide the ability to quickly say what are conditions currently relative to where they've been in the past to see if our current status is different from historical levels. The visualization should be accessible or understandable to the layperson, as well as being sufficient for the scientific audience to sort of quantify that information. We're also creating a dashboard for this that is 100% fully interactive, has maps and time series that you can interact with by zooming in, out, configuring different options to portray the information based on the information you or the details you want to know. And I'll show some of that later in the presentation. This is another way to look at our approach, and this is kind of just a workflow that we use for a lot of our different reporting products. But again, this is in line with our open science approach to not only expose the process, make it available to others, but make it automated and reproducible. So this is kind of the general idea here. We have working, developing the pipeline locally, but hosting it online on GitHub and employing some automated actions to update the dashboard on essentially what's going to be a daily time step to pull in information as it becomes available. When it's updated, then it gets pushed to the dashboard. And if something fails in this automated process, we get notified and intervene as needed. But really, once it's set up, it should work on its own and should only fail, for example, when maybe like the data format changes or something that requires our attention to fix the issue. Now, the distillation of this data to a local context required some custom-built software, as I mentioned earlier. So one of the data sets we're using, just as an example, is the Prism Global Dataset, which is a raster level product with global coverage that describes things like air temperature, precipitation, a couple other things. But our custom software, this TBEP Tools R package, has routines for importing these data, these global data sets, and summarizing it at a local scale so that it is portrayed in a way that is informative to our audience. And so we have breakdowns by different subwatersheds, Tampa Bay, and we can show it in a visualization that kind of describes essentially this what is the current status relative to the past. So we have these sliders that show to the right what is the current condition relative to a historical baseline. So you can see that, just from this example, looks like September 26th of last year was much hotter than the historical record for that day. On the landing page for the dashboard, we have these snapshot conditions that provide a quick overview of where we're at today relative to the past, kind of summarizing all of the indicators we've got on the dashboard. So you can look at air temperature now, rainfall now, ocean temperature now, storms now, and see where we are essentially today as a deviation from the long-term distribution of these values, just as a quick snapshot to get an understanding of what is the current condition. Now, of course, you can dive deeper into any one of these indicators by clicking the tabs above, and you can get information like this. And so this is just an example of the long-term time series for air temperature, showing you the current year in red, the year prior to that in orange, and then all of the previous years behind those. And so you can see essentially where we're at today relative to the past. And you can summarize this looking at the entire bay, for example, or different subwatersheds of the bay to get a more detailed spatial context. And you have the ability to summarize this in different temporal contexts. So what is the current year you're looking at relative to the baseline of interest? So you can change these based on whatever information you want. Similarly, you can do this for rainfall. This is the exact same setup, but showing the long-term record of annual cumulative rainfall for Tampa Bay in this example, with the current year and purple, and then the previous year and bluish, and then all of the historical record in those light gray lines. And a lot of these products are summarized, as I showed earlier, with these kind of interactive now versus then maps to see what's happening today relative to the past. And so we have these for multiple indicators. I showed you air temperature earlier, but here's ocean temperature, here's rainfall. And basically to the right of the slider is present, and then to the left is going to be historical. And so you can, again, get a quick idea of where we're at today. And you can change the historical reference period or what day you're looking at based on the information you want. And lastly, we wanted to look at storm frequency and intensity to get an idea of how that might be changing over time. Essentially, we have a buffer around Tampa Bay, and we were able to extract historical records of storm track and magnitude of the storms. So if any storm intersected this circle, it's going to be in the dashboard. And right now, it's just showing storms for the last 2 years, just to give an idea of how many we had recently. But you could change this to the whole record if you like. But another thing we wanted to look at was how essentially the frequency and intensity might be changing over time. So this graph here basically summarizes in any given year the number of storms multiplied by their relative intensity. So kind of just an idea of how that might be changing. And you can summarize it by this period, essentially looking at the average for a recent period of interest relative to the historical, just to get an idea of how that's changing. You could change that split as well to see different subsets of this data. So that's pretty much how we're thinking about this. We have these summarized in different ways, but our general approach to this is thinking about this in terms of how we want to meet different audiences, whether it be the public, managers or policymakers, or the broader research community. And so this is just an example of a dashboard that might be more appropriate for managers and policymakers, but because we have these routines broken up, or rather developed with open source software, we can easily serve this up in different formats like fact sheets or even more technical documents to serve different audiences. So that's the idea. That's our philosophy of how we approach this. And in terms of how this might affect the public, you think about how these indicators might lead to more informed understanding. So this is where indicators and reporting kind of fall in terms of how this might influence behavior. Really, what we want to see is not just better understanding of the problem, but that leading to, intentions to change one's behavior around how, we think about climate change and how individual actions of one might support the greater good, and then how they might change their behavior for the greater good. So this is just one part of it. We need other tools like social scientists to help with this, because that's ultimately where we're trying to go. So that's all I have for this talk. Here's a link to the source code for the climate change indicators dashboard, as well as some more general links about what we do as a program with data viz and data management and open science. So I appreciate your attention, and I look forward to hopefully seeing you all in person at the conference. Thank you.